you likely didn't displace today. And that's because you end up back here in your own bed. Sure, you woke up here, you may have moved around, and if you're really courageous in this age, you may have actually gone outside. So let's say you walked through a park, you got some groceries, and generally moved about town. And yet when you went to bed at the end of the night, you've not displaced over that entire time. So let's talk about displacement, how it differs from distance, and how it forms the core of some of those important physical quantities. Howdy everyone, I'm Biscuit. And to understand displacement, we first need to talk about the difference between displacement and distance. Now distance is likely what you expect. It's the total amount you've moved during a period of time. This is essentially the speedometer on your car or a step counter. For all this zigzagging, distance is how much mileage you're racking up. So distance is what matters when considering the gas you need or how much wear and tear is going to be on your body as you move about. Contrasting from that, displacement is just the difference from your final position from your starting position. If both positions are the same, like waking up and falling asleep in the same bed, this difference is zero. Hence, there's no displacement. To visualize displacement, you can draw a straight line that ends up being the shortest difference between 2 points, pointing from the starting point to the finishing point. Therefore, displacement is a vector, meaning there's a directionality to it. This means this vector's magnitude is the shortest distance between the 2 points, which allows us to connect the two concepts of distance and displacement together. Distances along paths can always be longer, but the distance between 2 points does have some minimum value, and that's what enters in displacement. Okay, I'm actually getting tired. I should get some coffee. Okay, so why should we care about displacement? Isn't distance just fine? Okay, well, so there's a few reasons. One thing is that displacement enters in a bunch of equations because the shortest distance between points matters, like gravitational pull between two objects, or the direction part matters a lot. The other really important reason is that many fundamental quantities use displacement to define them, not distance. Most notably being velocity. Velocity is defined as the change in displacement over the change in time. If you change a position over a set amount of time, you have to be moving. That's all that means. A vector is written out as a derivative over time, or you can think about the d's in the derivative being differences that are really, really small, infinitesimally small, with the points being so close together. So close, in fact, that a derivative represents a slope essentially going through 1 point. Meanwhile, speed is the time derivative of distance. Because of the whole infinitesimally small thing, the only difference between speed and velocity is the whole vector direction thing. But sometimes direction matters and sometimes it doesn't. For instance, the quantity momentum uses velocity because which direction you crash your car matters, while kinetic energy uses speed because how much gas you need to speed up doesn't matter which direction you're going. Coffee's done. Going one step further, we get the almighty acceleration, which is defined as the change in velocity over the change in time. So essentially is the time derivative of velocity. If your velocity changes, you're moving in a different direction, you have to accelerate. This then makes acceleration the second time derivative of displacement. Acceleration is important because like all the other stuff I've talked about, it shows up a lot. And acceleration is what you really feel in the world. You don't feel speed or position. Currently, we're whizzing by through space at incredibly high speeds, but you don't really notice because the accelerations that are involved with turning around the sun are really small. Or if you were on a train and you took away all the bumps, made it perfectly smooth, it'd feel like just being on the ground. I mean, you could close your eyes and not tell the difference. I mean, you could even argue that the trees and the buildings are the things moving outside, not you. And that leads to a whole can of worms about reference frames, and we'll probably say that for later. Meanwhile, you can actually feel acceleration, like if you're in a car that's speeding up, braking, or taking a hard turn, because all those actions accelerate the car, and the walls and the seats need to accelerate you and push you to keep you moving in the car. Otherwise, you just go flying out. Okay, I got coffee. Hot. So displacement is an important quantity. It shows up in numerous equations and is used to define some of the most important physical quantities, like velocity and acceleration. And many of us don't end up displacing during the day since our starting and our ending points end up being the same. So hopefully we'll get to a place where we're able to displace safely in the future. Okay, in the meantime, appreciate you all watching. Okay, thanks, bye. Hot.